Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the angle, sum and difference formula. So there is one for sine, cos and tan. Now just a word on how you read this. So if you see a plus here on top, it means it corresponds to the plus on top there. So sine of alpha plus beta, sine alpha cos beta plus sine beta cos alpha. Now it's the opposite way for cos. So we've got a plus here, it corresponds to the minus. So cos alpha plus beta is cos alpha cos beta minus sine alpha cos beta. Plus goes with this minus goes with this plus. And similarly for tan. The plus is written on top, so when it's a plus, you have a plus here and a minus here, and so on. So these formula, where would they be useful? Well, firstly, we can come up with formula for things like double angles. So sine 2 theta is called the double angle formula. We can derive it from this equation up here. So theta plus theta equals 2 theta. So I'm just going to write it as sine of theta plus theta. And from the formula at the top, we're told this is sine of the first, cos of the second, plus sine of the second, cos of the first. In this case, the first and second are both equal to theta. So it's just equal to 2 sine theta cos theta. So that flowed very nicely from the angle, sum and difference formula. Let's look at another application of them. So the angle, sum and difference formula also help us calculate exact values. Now we already know exact values when the angle is a multiple of 30 or 45, but we can actually calculate the exact value when the angle is a multiple of 15 degrees. So we can do that with something like cos of 105 degrees, and we're going to use this formula here. So how do we do it? Well, what we want to do is we want to write this as the sum or difference of angles whose exact values we already know. So we know the exact values of sine and cos of 60 and also 45. So we're going to write 105 as 60 plus 45. Now using this formula here, the same one that was on the previous slide, that's just going to be cos of the first times cos of the second minus sine of the first, sine of the second. Now we already know all these exact values. We know that cos 60 is equal to a half, cos 45 is equal to 1 on root 2, minus sine 60 is root 3 on 2, and sine 45 is also 1 on root 2. So what we can do here is make these things into one fraction. So 1/2 times 1 on root 2 is 1 on 2 root 2 minus root 3 times 1 over 2 root 2. And we'll just combine it into one fraction. We only add or subtract the numerators and we keep the denominator the same. So this here is the exact value of cos 105. So let's do something similar for tan of 17 pi on 12 radians. Now, a lot of people find degrees a lot easier to work with, so it might be better if we just write this in degrees. So if you want to convert 17 pi on 12 radians to degrees, you times by 180 over pi. We actually then get 255. So tan of 17 pi on 12 is equal to tan of 255. So once again, we're going to write this as the sum or difference of numbers whose exact value we know. So we know the exact value of tan 225. It's the same as tan of 45. And then we add 30. So using this formula up here, we would have, it would equal tan of the first, so tan 225 plus tan of the second, all divided by 1 minus tan of the first times tan of the second. So we know the exact values of tan 225 and tan 30. Tan 225 is just 1. Tan 30 is 1 on root 3. So this will be 1 over 1 on root 3 all over 1 minus 1 on root 3. So that is the exact value. We might just want to clean it up a bit. So we can make these into one fraction. 1 is just root 3 on root 3. So what I can do is I can rewrite the top as root 3 plus 1 on root 3, and the bottom will be 1 minus root 3 all over root 3. Now when you have a fraction like this, the two root 3's cancel out. You're just left with root 3 plus 1 over 1 minus root 3. That's good enough. That is the exact value. All right, let's look at another example where we can use angle sum and difference formula. Another benefit of the angle sum and difference formula is that they allow us to prove trigonometric identities like this. Now we know this one, we saw this in the ambiguous case of the sine rule. Remember, if we got an answer of theta, there was another answer of 180 minus theta, and that's because if you take, say, sine of 30, you get the same as sine of 150. Sine of 20 is the same as sine of 160. We also sort of saw this when we were doing the unit circle. But we can easily prove this now. Now, you might get freaked out by the word prove, but this is remarkably easy given this formula. So what I'm going to do is expand this using this formula up there. So sine of 180 minus theta, it's just sine of the first times cos of the second minus sine of the second cos of the first. Now, of course, we know that cos of 180 is negative 1, sine of 180 is just 0. So making those replacements, I just get this. Okay, now, of course, 0 times cos theta is just 0, and of course, a negative times a negative is a positive. This just equals sine theta, and we've proved exactly what we want to. All right, let's now look at a harder question involving angle sum and difference formula. So we're going to write this expression in this form here. So this already starts to look like cos of alpha plus beta, because if you expand this, you get cos of something times cos of something minus sine of something times sine of something. The problem here is we can't find something so that cos of that equals 5. Cos of theta equals 5 has no solutions, because cos theta always lives between negative 1 and 1. So how are we going to do this? Well, we're going to use a bit of ingenuity. What we're going to do is take out a factor that is the square root of the sum of the squares of the two numbers, 5 squared plus negative 12 squared. So if you put that in your calculator, you get 13. We're actually going to take out a factor of 13. So we write it as 13 times 5 over 13. Of course, that equals 5. Cos x minus 12 over 13 sine x. Okay, so why did we do that? How is that possibly going to help? Well, clearly we can easily solve cos theta equals 5 over 13. In fact, we can just put that in our calculator. Theta equals cos inverse of 5 over 13. So putting that in our calculator, we get 67.4 degrees. It really wouldn't matter if we had the answer here in radians. Okay, so does that help us a lot? Well, yes, it does. By taking out this factor here, we have this squared plus this squared equals 1. 5 on 13 squared plus 12 on 13 squared equals 1. Hopefully that looks familiar, because we know sine squared theta plus cos squared theta equals 1. The point is that by doing it this way, this will also work for sine. It turns out that sine of 67.4 will equal 12 over 13, exactly what we wanted. So we can rewrite this as 13. Now 5 over 13 we can write as cos of 67.4, and we can rewrite 12 over 13 as sine of 67.4. And hopefully you can see now this will just be 13 cos of x plus 67.4. We're just going the other way now than we have been going. Instead of expanding it, we're kind of like factorizing it. And then we're done. If you expand this, you will get this, which is equal to this. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.